A warm greetings to one and all. In this session, let's learn about ridge regression with an example.
As a part of introduction, we all know that maximum likelihood estimation can lead to overfitting because it finds the parameter values that best fit the training data, which may result in complex model, especially when data is noisy. In linear regression, if variables are highly correlated, it becomes unstable and yield unreliable estimates. Ridge regression resolved this problem by introducing regularization concept, which penalize a large coefficient to stabilize the model and reduce the problem of overfitting. Ridge regression is a model tuning method that is used to analyze the data that suffers from multicollinearity. This model performs L2 regularization when the issue of multicollinearity occurs, least square are unbiased and variance are large. This results in predicted value being far away from the actual values. Multicollinearity occurs when two or more predictor variables in a regression model are highly correlated, which leads to unreliable and unstable estimation of regression coefficient. We know that multicollinearity occurs when two or more predictor variables in a regression model are highly correlated, meaning that they contain similar information about the variance in the response variable. This can make it difficult to determine the individual effect of each predictor on the outcome, leading to unreliable estimates of regression coefficients. Let's have a simple example. Suppose you are predicting the house price using two features, namely size of the house and number of rooms. The size of house and number of rooms are likely to be highly correlated because a large house typically has more rooms. If you include both of these variables in a regression model to predict the house price, multicollinearity may arise. This can cause the regression coefficient for these variables to be unstable and difficult to interpret because the model cannot easily distinguish their individual contributions to predict the house prices. Effect. In the presence of multicollinearity, the standard errors of the coefficient may increase. The model may give misleading significant tests for the predictors. Small change in the data can lead to large changes in the model. Now let's learn about bias and variance trade-off. First, let's check out the underfit model. So here in the training phase, the model is too simple to capture the pattern in training data. This leads to high bias, whereas in testing phase, it performs poorly on both training and testing data. It shows low variance because it is not complex enough to adapt the fluctuation in data. So next, let's check out the overfitting model. So here in the training phase, the model is very complex and fits the training data too well, even capturing the noise. This leads to low bias. In testing phase, the model performs poorly on new and unseen data because it over-adapts to the training data. It leads to high variance in testing phase. So next, let's check out the well-fitted or optimal model. So here in the training phase, the model captures underlying patterns in the training data well with the low bias value. Whereas in testing phase, it generalizes well to unseen data, balancing the complexity and flexibility. So it results in low variance. So hope you're clear in bias and variance trade-off with respect to underfitting, overfitting, and well-fitted model. We all know that ridge regression is a procedure for eliminating the bias of coefficient and reducing the mean square error by shrinking the coefficient of the model towards zero in order to solve problems of overfitting or multicollinearity that are normally associated with ordinary least square regression. Ridge regression allows control over the bias variance trade-off as we have seen in the previous slide. Increasing the value of lambda increases the bias but reduces the variance. So while decreasing the lambda, it does the opposite. The goal is to find optimal lambda that balances bias and variance, leading to a model that generalizes well to a new data. The formula for ridge regression is beta cap is equal to x transpose x plus lambda I inverse x transpose y. This technique is known as ridge regression or penalized least square. In general, adding a Gaussian prior to the parameter of a model to encourage them to be small is called L2 regularization or weight decay. Now let's have an example to solve a ridge regression problem for the given data set, and we need to fit the linear model y is equal to beta naught plus beta 1 x using ridge regression. So in step 1, we need to define the data set. We are given the following data, that is x and y. The values of x are 1, 2 and 3 and the values of y are 2, 3 and 4 as we are given in the input. So now we need to fit a linear model y is equal to beta naught plus beta 1 x using ridge regression, which applies regularization to avoid overfitting. In step 2, we need to formulate the design matrix x and response vector y. So the design matrix S is nothing but a matrix where each row corresponds to an observation and each column corresponds to a feature. Response vector Y is a vector containing the observed Y values. So for the given data set, we know the value of X is equal to 1, 2, and 3 and Y value is equal to 2, 3, and 4. So here we need to construct the design matrix X by adding the column of ones for intercept. So we know the value of X is 1, 2, 3. Here we are adding 1, 1, 1 as a column matrix because this 1 represents the intercept value. So along with the intercept value, we are adding the X value, that is 1, 2, and 3, which is given in our data set. Then Y is equal to 2, 3, 4. So this is what represented here in this column matrix. In step 3, we need to calculate ridge regression coefficient. So now let's compute the coefficient beta using the normal equation. We plug in the values where x is the design matrix, y is the response vector, and we initialize lambda is equal to 1 here. It is the regularization parameter, and I is the identity matrix. The equation we need to compute is beta is equal to x transpose x plus lambda I inverse into x transpose y, where the design matrix x value was 1, 1, 1, 2, 1, 3, and the response vector y value was 2, 3, and 4. It is a column vector. Now, if we substitute the value for computing x transpose x, we'll be getting the value of x transpose is nothing but transposing the x value. The x value we know that it is 1, 1, 1, 2, 1, 3. If we transpose this, we'll be getting it as 1, 1, 1, 1, 2, 3. And we are multiplying this with the x value, that is 1, 1, 1, 2, and 1, 3. We'll be getting the value as 3, 6, and 6, 14 for the term x transpose x. In next step, we need to add the regularization term lambda I. That is x transpose x plus lambda I. In previous step, we have calculated x transpose x. The value was 3, 6, 6, 14. The value for lambda is initialized with 1. So we have written it as 1. It should be multiplied with the identity matrix value, that is 1, 0, 0, 1. So if you multiply 1 with the identity matrix, we'll be having the same value of identity matrix, that is 1, 0, 0, 1. So now we need to add x transpose x value with lambda I value. So we'll be getting 3 plus 1, 4, 6 plus 0 as 6, 6 plus 0 as 6, 14 plus 1 as 50. So this is the value for the term x transpose x plus lambda I. So next we need to find inverse for the same term. So if we find inverse of 4, 6, 6, 15, we'll be getting the value as 5 divided by 8 minus 1 by 4 minus 1 by 4 and 1 by 6. Next we need to compute the value for the term x transpose y. So we know the value of x transpose. The value is 1, 1, 1, 1, 2, 3. So we have written it here. The value of y is nothing but response vector matrix, that is 2, 3, and 4. So we have written it here. If we multiply these two matrix, we'll be getting the value as 920. So in order to get the value for beta, we have to multiply step 3 and step 4. So in step 3, we have found the value for the term x transpose x plus lambda I inverse. So that is what which we have obtained here. And x transpose y is being computed in step 4. The value is 920. So if we combine these two results, the beta is equal to 5 by 8 minus 1 by 4 minus 1 by 4, 1 by 6 into 920. This is equal to 0.625 and 1.083. Here, beta naught value is 0.625 and beta 1 value is 1.083. So the final result is we need to fit the ridge regression model, that is y is equal to beta naught. The value is 0.625 plus beta 1, that is 1.083 into x. So this is the final model incorporating the regularization to prevent the overfitting. So hope you are clear in this example for ridge regression. Thank you all.